Alright, so today we're going to be solving questions on dimensional analysis. The first one says determine the dimensions of surface tension, Young modulus, universal gravitational constant, viscosity, pressure gradient, velocity gradient. Alright, academic data. So for surface tension, we use a coiled Y to represent surface tension. And we say that surface tension is the ratio of force to length. So force over length is surface tension. And we remember that from Newton's second law, force is equals to ma, length is L. So by method of dimensional analysis, mass remains mass because dimension is the measurement of physical quantities using mass, length, and time. When we get to thermodynamics, we now add three more, which is current, amount of substance, and temperature. So mass. Then we know that acceleration is the change in velocity all over time, which is Lt raised to power minus 2. So this is the dimension of force all over L. Now, when you apply the law of indices to this question, you see that we can apply division law here. Apply division law so that this becomes M. Then half L. Now, there's an invisible one here, there's an invisible one here. Division law states that when the bases are the same, subtract the power. So I do 1 minus 1, T minus 2. So that this becomes ML0, T minus 2, which is the same thing as saying M times anything raised to 0 is 1 times 1 times T minus 2, which is the same thing as mt raised to power minus 2. So that is surface tension for you. So surface tension, the dimension of surface tension, the dimension of surface tension is simply mt raised to power minus 2. And that means that the units is the same thing as saying mass is kg, time is seconds raised to power minus 2. So the unit of surface tension is kilogram per square seconds. So that is for surface tension. Alright, let's move to the second one. Second one is Young modulus. Young modulus. So we say that Young modulus is the ratio of stress to strain. Or we say it is the pressure due to extension. So we know that stress is the same thing as pressure, and it has the formula of force per area, force over area, while strain is simply extension all over original length. Strain is simply extension all over original length. So like I said in class, anytime you're doing all these things, know that the one that should come at the denominator is the normal one, as in the normal place. Original length, before you have extension, you should have original length. Just like density, before you talk about body, should I say, you will have a container for it, which is the volume. That is why it has mass over volume. So the same thing with force over area for stress. Before you talk about force, there should be an area that the force is acting on. So the main thing stays at the denominator, while what happens afterwards stays at the numerator. So let's tackle stress. We say that stress is equals to force over area, which is the same thing as saying mlt raised to power minus 2 all over L raised to power 2. You know that area is the same thing as saying vertical and horizontal axis. L, that is meter, length this side and this side. So length square. Y volume is the same thing as saying 3 dimension. Length here, length here, length here. L. 3 times. So but we are dealing with area. So we move ahead. So notice that over here we have L square, we have L. This is L raised to power 1. So applying division law of indices, we have that this is ML 1 when these two, if since the bases are the same, you subtract the powers, so T minus 2, so that this now becomes ML raised to power minus 1 T raised to power minus 2. So that is for stress. That is the dimension of stress. Now for strain is length, or should I say extension? Let me use extension. Length extended, or we say extension all over original length. And we know that all this is L over L. 2 divided by 2 is 1. Anything divided by itself is 1. So this is simply 1. And we know that anytime we have 1 in physics, we say that all dimensionless constants are equals to 1. So strain is a dimensionless quantity. So it's equals to 1. So let's go back to our Young modulus. So for that reason, Young modulus is simply, let's apply what we have for stress. ML raised to power minus 1 T raised to power minus 2 all over 1. Which means anything divided by 1 is that. Which means that Young modulus is simply equals to stress. This is our answer. And if we progress to putting this in indical form, we have that this is M1 over L 1 over T raised to power 2, which is the same thing as M all over LT raised to power 2. That is applying indices. So this and this, they are the same. So that's our final answer. Now for universal gravitational constants, which is the third one. The third one says universal gravitational constant as the third one. So to find universal gravitational constant, we need to first of all remember that Newton's law of gravity states that F is equals to Gm1 m2 all over r square. And we know that this is the same as saying Gm square over r square. So in order to get G, this gravitational constant, we need to make it subject of the formula. So when we make it subject of the formula, it's simply doing anything standing on this one is over 1 cross multiply, so that you get F r square is equals to Gm square. To make G subject of the formula, divide both sides by the coefficient, which is m square. So when we divide now, you see that we now have G to be equals to Fr square over m square. So it's at this point we now substitute. We know that F is equals to ml t minus 2. R is the same thing as distance. Radius is distance found in a circle. So L square all over m square. So when you do it properly, collecting like terms, you know that this is the same thing as m, not like terms, applying multiplication law to the multiplication law of indices to the numerator, we have m l1 plus 2, then t minus 2 all over m square. which is equals to ml3 t raised to the power minus 2 all over m square. Now notice that if this is m and m, the bases are the same. We can apply division law there, so that we have m1 minus 2 l3 t raised to the power minus 2. So that this now becomes m minus 1 l3 t minus 2. So that will be your answer. So, but if you take this to indica form, this is also equals to the sentence saying 1 over m l3 1 over t square, which is the sentence saying l3 all over mt square. So whichever one is the same thing. Alright, so let's move to the fourth question. The first question is talking about viscosity, and we know that viscosity is simply the ratio. Viscosity represented this way is simply the ratio of force to the product of area and velocity gradient. So viscosity is the ratio of force to the product of area and velocity gradient. So now remember that force is m lt minus 2 and area is length square. Then I want you to know that anytime you hear velocity gradient, is the same as saying velocity over length. If you hear pressure gradient, is the same as saying pressure over length. The gradient of anything is simply that particular thing over length. If you say Ronaldo gradient, is the same as saying Ronaldo over length of Ronaldo. So for that reason, I'll have velocity first of all is lt minus 1. Lt minus 1. So all over L. That is what velocity gradient is. Velocity over length. So now notice that this is now the same as saying mlt minus 2 all over L. Now the same as saying L square, then lt minus 1 L raised to power minus 1. Because anything at the denominator, if you apply in this law, this is the same as 1 over L, which is L raised to power minus 1. So collecting the powers by product law, I will have mlt minus 2 all over L square plus 1. Since the bases are the same, you add the powers, minus 1 t raised to power minus 1. So this becomes mlt minus 2 all over, this is 3 minus 1, 2 L square t minus 1. So this is now the sentence saying applying division law now. Applying division law will get that this is now the sentence saying ml1, when this 2 comes up, minus 2, and t minus 2, when this comes up, it becomes minus minus, so which is plus 1. So equals to ml minus 1 t minus 1. And this is also the same thing as having m1 over L 1 over t. which is the sentinel saying M over LT. So this is the sentinel with this. We applied indices law to it. So this is 1. This is 1. So that is for viscosity. ml raised to power minus 1, T raised to power minus 1. So for pressure gradients, which is the same as saying pressure gradient is the same thing as saying, let's say find number 5. Pressure gradient is the same thing as saying pressure over length, which is the same thing as saying force over area all over length, if you remember. So this is going to be the same thing as saying ml T minus 2 divided by L square all over L, if you remember. And I think we've done pressure before when we did stress. Let's get what we have here, so we don't stress ourselves. So it's going to give us ml minus 1 T minus 2. But if you want us to do it together, so we get ml minus 1 T minus 2 all over L. That is doing indices now. This one that is divided, when you bring a division law here, 1 minus 2 minus 1 over L. So this at this point we'll now have division law again. This will now be ml minus 1 minus 1 then T minus 2. So that this becomes ml minus 2 T minus 2. So this is my final answer if it's objective. But if it's theory, I would advise you still apply your indices law, so that this becomes ml 1 over L2 1 over T square, which is the same thing as saying M over L2 T square, L square T square. So if it's theory, I leave my answer this. So objective, this is the same with this. So that is for pressure gradient. Thank you very much.